What is happening with this? Due to a maintained smooth streaming. Don't care. Okay. Error. YouTube is not reserving enough video to maintain it. Okay, no. The quality should be good now. Can I switch off this warning? Open widgets. What's this? Error. Poor status. No, the stream should be fine. I'm seeing the video. It's good enough. Don't know. Not receiving enough bandwidth. Yeah, it's okay. Let me listen to the sound actually. So, yeah, sound works. I think works. Let's continue with. So first off, what you're watching right now, the cat. That's a lucky cat. That's normally something you see very often in Asia, particularly in China, which brings you fortune. But it's very useful to know if the camera is working, because this is moving all the time. And if it's not moving anymore, you know you have an issue with the camera. And that's why I use this. This is the Winkkatze. At least that's how it's called here. And I got it from the people who do the conference talks for the CCC, and I help them sometime, and they have this really clever idea to put Winkelkatzen to test if the stream work. So last time we had this. So we're on this stream. We'll continue with the IOVoodoo long stream about the reverse engineering debugging tool. Yeah, reverse engineering tool. And the issue with that was that the pinout on the USB was reversed because I didn't pay attention, and it wasn't written in the datasheet, and I didn't pay attention, but the pinout was from the backside and not from the top view. So it was a bottom view, not from a top view. This is why it was reversed. Things I should know. I've made a mistake, and I will probably still make it, but the more I get bitten by it, the less I will make it, hopefully. So this was, we stopped here because the USB wasn't working correctly, because the pin was reversed. I've ordered some new boards. These are the new boards. And we will continue with that. And so, let's take one of the old boards, because I did tiny modifications, not a lot of them. This is one of the new boards. The main modification you see was about the text. The text is a lot larger and it's a lot more readable. Can I switch the camera this way? Yeah. The text is a lot more readable. You can see I've increased the font size, and what I've also changed, what you see less, you see here. This is how I track my numbering. Here on the versioning, you see 0.10 and then a hash. 0 means it's version 0 because I didn't make any lots of modification. The prototype always starts with 0. 10 means the board layout has been touched at least 10 times, or the schematic. You see here I did some modification, so now we're 0.14, meaning I've touched the board or schematic layout at least 14 times, and we have another hash. This way in my Git history I can check out what exactly Git's revision this board corresponds to. This is how I do my tracking, and then the date is auto-generated. You see it's 2 weeks afterwards. I created a new one because it takes around 2 weeks to arrive. So the font is the first thing I changed. It's a lot more readable, it's a lot more concise. That's good. I know that this 100% font is not very good. This is 150% font size. You can also read the logo more, and here my open source hardware logo, it's also a lot bigger, and also my credentials are a lot bigger. And I've added the seal screen for the programming header here, prog svd, because you use serial wire debug to program it. And you see we have the pinout, very important because there is no common pinout for svd, so you always have to check. This is the thing. But these are the minor improvements. The major improvement I did is here. I fixed the routing. Does it look like? Yeah, I fixed the routing. Yes, I fixed the routing from the USB. You don't see a lot of differences though. Let me zoom. You don't see a lot of differences. The traces look almost identical. It's just that now on the new trace, because the lines are inverted, I had to go down. So one of the pain points now is that normally USBs well, it is a differential line, not 100%, but almost 100% is the differential line, and you should keep the length the same way. Here, the lengths are not exactly the same, and they are not exactly next to each other for some time, like on this side when going out of the TVS diode. But we will test if it's good enough. It is USB 2, but it is full speed and not high speed, so I hope it works. Although, does it make a difference if it's full speed or high speed for the protocol? I don't know. Well, we'll check if it works. I'm not really that good with differential signals. So this is the old one, right? Yeah, small font. This is the old one. Let's put the old one to the batch of PCBs I will probably never have allocated again. And I have a huge box with plenty of projects which are yet broken or several prototypes before. I just didn't need 5 of them. Here you see, I have still 5 of them. I don't have the parts to have 5 of them, so we can play with some. And now it's time to assemble, and I will not make the exact same mistake as last time. I will try to solder a bit cleaner, so you will not see everything, because soldering under the camera is really a pain, and I wasn't aware of it completely. Now I'm a bit more aware of it. I'll still explain what I'm doing. So we need to start again with the USB and the power supply like we did the last time. So let's get all the parts. I didn't prepare anything on the parts. I wanted to stream because I received them very recently. So we need USB here, USB box. Then we need some resistors. Not resistors, I know. We need some capacitors, 100 nano capacitors. For that, I have an assembly tray. This one. This is an assembly tray from Unexpected Maker. Yeah, Unexpected Maker makes them. You print them, you laser cut the acrylic, and then you have small parts. And jelly bean parts like this, for example. Here the 100 nanofarads decoupling capacitors, I have plenty of them here, so I'll use it from the tray instead of using them from the bag. Else I will have too many bags on top. But I don't have all the resistors in there, so I need to have my box of resistors. Here, resistors over 1K. Yep, resistors over 1K. Then we also need, so we have USB, we have resistors, decoupling capacitors, LEDs, there I don't need. ICs, I need a voltage regulator. So this is my power book, and in there I have my voltage regulators. For now, that's good. I think we should be fine. Let's fire up the soldering iron. I'll use the main one. And let's start. Here we have some. This is just a syringe with lots of flux. If you do FSMD, flux is like lubricants. You can't have enough of them. It's a pain to clean if you have too much, but you can still clean it, and it helps really a lot when you solder stuff. So, USB, it's not on this bag actually. I have a USB. I forgot about that. I do have a USB SMD book. USB SMD book. And this SMD book includes the USB parts here. This is USB 16 pins, USB-C 16 pins. This is C 16 pins. These are the ones. Up. Let's take some tweezers. Soldering iron is on the way. I just need one of you for now, and I hope that USB is working, and then we can debug another thing. I'm sure we'll have other bugs. This is what prototypes are for. Up, USB gone. So I will incline the camera so you can probably see what I'm doing, but it will still rather be near me, so I can see myself how I'm soldering. We have 2 resistors, they come afterwards. First, let's solder that. Flux on SMD pins. Camera, it's in focus. But you see the, can you, no it's not, did I switch? Yeah, I did, so you don't see it, good, the camera is fine. Soldering iron heat up, and let's see if I can solder the pins correctly. And I'm doing some drag soldering. This is what this kind of bevel tip, you don't see it. It's not a chisel tip, it's kind of a bevel tip. This is really useful for drag soldering. For the rest it's a bit harder to use, but I'm too lazy to change it all the time, and I got used to this tip. For SMD drag soldering, it's perfect. Seems fine. Let me have a look. Yeah, it looks fine. So now we have to connect the 2 resistors, and then we can try again if we receive 5 volts. This is what I explained last time. These pull-up resistors, pull up or pull down resistor, will tell the device that there is a device here and that you should provide 5 volts if you do it correctly. If you use really USB-C, if you have a USB-A to USB-C adapter, you always see the 5 volts. And I think these are 1.5K, right? We're checking the bill of material. None. 1 R1, R2. Is it R1, R2? No, 5K1. 5.1K. The opposite, not 1.5. 5.1K. Yeah, 5.1K. We only need 2 of them. 1, 2. And I think I will never run out of these. Thousands. It's really a lot. But my less than 1,000 makes little sense. Have tweezers here. $5.1K. It is flipped. That's the pain of these. Oh, I didn't prepare a real USB-C cable or a real USB-C connection. I only have this cheating A to C, so I cannot test it correctly if it works. Let me try to get a real USB-C. Okay, these are the 2 parts, and now we can measure the 5 volts. This should be 5 volts right here, and then ground, and this should be the 5 volt coming out of USB. So let's try it first with normal USB. Well, normal USB. USB-A port to USB-C micro here. This is my power supplies. Here we have micro USB, and I need an adapter. Okay, I lost it. It should be somewhere. Here it already is. This is connected to my computer, but I don't want to connect to the computer yet. So I want to connect to my power supply, and my power supply will tell me if it works correctly, because I don't want to have shorts on my PC. Here I have no shorts. I should have tested it. That's what I can show you. I will show you the multimeter, and this way it's for you easier. So let me prepare the multimeter. This can be gone if it works. Let's see if the multimeter works. Data. UT up. Oh, the multimeter seems to work. Let's try if the power supply works. Welding for power supply. Serial to power supply not available. Yes, I didn't switch it on. Up, serial on. Serial to power supply works. And now let me give you my dashboard with all the tools. Measure. It seems to work. Damn it. This tiling window manager, I need this way. Now F11, not full fonts, and now what is it? Okay, connected. Okay. So now you can see it, and I should have tested with continuity mode. Here we are in ohms. Let's check the resistance. It is connected, so it seems to work fine. But here. So let's check between this line and this line. Yeah, high impedance. They are not shorted, at least on the pins. If we connect here, let's go to volts. And if we measure the voltage, we have 5.2 volts. That seems fine. Let's connect to the computer. This is using micro USB and not real USB-C. So we should have 5 volt no matter what happens. Up. And we have 4.7 volts. That's on the low side of USB. 4.75 volts would be, but now we have 4.6 volts. Minus because I reversed it. For the multimeter it's not important. And now I want to try with real USB-C. Let me get a USB-C cable. USB-C. Here's a cable, and I need to find a USB-C port. It should be somewhere on the back. Somewhere here is USB-C, if I don't mistaken. So you don't see anything, but I'm twiddling on my computer. I hope I didn't break the stream. No. Now I need to check if my USB-C port works, because last time we had an issue with that. I had an issue with that. The USB-C didn't work. Do I have an USB-C device? Yes, I do. Dev boards. Be patient. Here. I'll use this dev board, which has a USB-C connector, and if I connect to it, I should see USB serial. Yes. You don't see it, I do see it in my journals, my system journal. The USB-C works out of my computer. Now we can really test if USB-C works here, and if we have 5 volts, and if we have that, it means that at least this is correct. 5 volts, again minus because the wrong way around, but at least this is fixed. We don't know if USB-C work, or if USB, the data line work, but at least we know that the power is correct. So it was really just me messing the footprints. Yeah, that's an issue you can have if you create your own footprint library, but at least you know where the error could be and it's easy to fix. So let's solder the USB-C connector, which is really meant for surface mount soldering and not through hole, because the tabs are really short. You see it's a 1mm board and still the tabs don't go through it because the tabs are just 1mm. Meant for surface mount and for very small resistor. USB-C is connected. Before we connect, we have plenty of devices to connect. Let's connect the power supply, all this side. So C10 says 100 nano. I know it. I don't have to check on the things, but I can. Do I show you the bomb? The bomb takes a bit of space. No, I'll just do it myself. So 100 nano. Up. This is 100 nano. Yeah. 100 nanofarad. I have plenty of them actually. I could populate most of them. Don't be afraid to turn the table. Actually, I could use the turntable. Maybe it works better than this because I don't have a lot of surface mount components. This holder is good if you have surface mount component because you can flip it around and then solder the through hole component, sorry. And this will be through hole component which we'll need to test, but for now we don't. So I can use this table and turn it. And now I can turn how I wish, which makes it a lot easier to solder. We can zoom a tiny bit so you can partially see what I'm doing. Up, let's, for now it's okay. So this is the 100 nano. Second part soldered. Let's take the first part, first leg. This is the fuse, but we have other, no, these are 1 micro. Right one. 1 micro, 1 micro, 1 micro, 1 micro. Yeah. So we need capacitors, larger ones. But first the fuse. Let's look at the SMD book, and we need a 0.5 polyfuse. This is F1. And no, I'm not soldering with an ESD strap on. Currently there are not a lot of components which are sensitive to ESD issues. So I won't be able to create a lot of them. Up. Okay. Now we need 1 microfarad capacitors in 0603. So here's my capacitor box. 1 microfarad. Oh, we have some. I have some loose. This is nanofarads, but what size is this? Or 805 probably. Yeah, oh, even larger than 0805. Oh, 1206. I have 1206 100 nanofarad. I'm not sure when I will ever use it. And 0805, but they're too large. 1 microfarad. No, let's use the correct parts here. 0603, 1 nanofarad, or microfarad, sorry, microfarad. We need 1, 2, 3. We need plenty of them, also for this board, but that's for afterwards. We need 4 of them for the voltage regulators. So let's take just 4. 3, 4, and I should actually also empty this in the tray. So I need this, so I don't have to get the capacitors in the capacitor box all the time. I need this, I need this. This is just paper which sticks, and We'll see exactly what it's used to. Up. Now on this sticking paper we will write the specifications of this capacitors. (0603) 1 microfarad, 16 volts, X5R, but X5R is just the temperature rating. What is the tolerance? It's not there. It's not there. I could have a look at the data sheet. I don't really care. I think they're fine. So, take this sticker. Up. We stick it inside a box, so we have a label on what part it is. Then we use the tray, and now we empty it. And now for the next project, which needs 1 microfarad, we will have a tray. Up. Yeah, I recommend this this holder and this for assembly, single prototypes. It's quite useful. So I don't need this bag anymore. Trash. I don't need this paper anymore. Go away. This is in the way. This I don't need anymore. I don't need the pen. Let's put it somewhere where it's not in the way. Up. One, two. I can actually put solder on most of the pads. So this is the power. You don't see what I'm doing here. These are the power pads. This is the power section, and I need to put the resistors on the power section. 1, 2. 3. 4. Counting always helps, because then you remember how many parts you have to assemble. 1, 2. But I'm surprised. So now the voltage regulator are quite good. They work with 1 nanofarad, 1 microfarad. 1 microfarad capacitors, ceramic capacitors, which you can have at ceramic capacitors. Previously, for voltage regulators, you needed at least 2.2 microfarads, and for the 2 microfarad, that's the limits. That used to be the limit for ceramic capacitors. Now ceramic capacitors can go up to 10 easily. But it used to be the limit, and you had to use tantalum capacitors, which are a lot more expensive. But now you don't need anymore, which is a good thing. You can use ceramic, less expensive. Good enough. So now we need the voltage regulators. I don't remember which one is which one. I think U14 is the one. U4. Let me put up this way you can see the bill of materials. And I will just move away this overview. So U4, which one is it? Yeah, U4 is 1.8 volts. If I wanted to be professional, if I want other people to assemble this, I could create a program which tells you all the time, you place this, place this, place this, and then you just press on space button and it goes to the next item. But it takes a bit of time to do it. I don't need it for this case. So we need one of, where are they? Boost inverter? No, no. I know it's 3 legs. This is 3.3 volt. That's a step up. 8 volts. I know I have plenty of them. That's 3.3. That's here. Oh, you can only see it on the mainstream, on the overview cam, the dashboard. So this is 1.8 volts. This goes here, and then we have 3.3 volts. This one. Three 3 volts. And the 5 volt is completely unregulated and comes directly out of USB. So according to the USB specification, it's plus minus 0.25 volts, but it could be even more. And we use the 5 volts to power most of the device actually, because the microcontroller has the internal voltage regulator, and I need 5 volts because, yeah, part of the design is to be 5 volt tolerant, so I need 5 volt as input. And I unregulate it because the regulation removes a tiny bit of the voltage. Even if the LDOs, low dropout voltage regulators, linear regulators, I don't know, are all voltage regulators linear regulators? I call voltage regulator anything which gives me which changes the voltage of a line. But I don't know if in real voltage regulators are just meant for LDOs. Don't know. Sold that. And yeah, low LDOs, low dropout, have a low dropout, something like 0.3 volts, but they still have a dropout voltage. So the 5 volt would even be reduced lower, which we don't want. Not ideal soldering, but it works. So let's measure the outputs. Let's connect the 5 volts from our power supply. And let's measure the output voltages. Up. And ground we have here. This should be 1.8 volts. 1.8 volts. 1.81. That's good. It's precise enough. This should be 3.3 volts. There should be no short. 3.2. Yeah, 3.3. If I touch it, no, it doesn't get warm. It's probably the residual warmth of the soldering, but else it's not very warm. So that works fine. This is a good advantage. This is starting to look good. Now, what can we do? What will we do? I think we have to start with the microcontroller. Well, how you assemble very often. So, when I do a prototype, I assemble first part by part. Now that the voltage works correctly, I can move to the next part. The next part is everything which is microcontroller. But generally, when you want to assemble surface mount devices, you start from the middle to the end, and go to the edges. Because when you go with your soldering iron, if there's something you've put on the edge which is really high, like electrolytic capacitors, then you're on the way and it's really a pain to solder. If you do it from the middle to the outside, you don't have this issue. So let's put the microcontroller on it. It's the only one I have. And then we can put all the capacitors. Some I don't think there are a lot of very important resistors, but there are some optional resistors for to reset default state and things like that. I need to put it. I don't solder the USB yet because we can still solder it afterwards, and I want to taste JTAG first. So, microcontroller. Up my microcontroller. SMD book with plenty of non-through-hole microcontrollers, and I should have one. Yeah, that's the only one I have. It cost a bit much to have plenty. And yeah, so SMD book, so I've ordered it from DigiKey. You recognize the label. I still cut this label from the SMD bag, and I put it in another smaller SMD bag. And I keep this, how's it called? Moisture indication. Yeah. I don't have any issue here. I'm in Europe, Germany, and we don't have a lot of issues with moisture. I'm not living in a very damp thing, but I still keep the moisture indication, and this way we can see if it's good or not. Here. Bake part, if not blue. This is blue. Bake part is not blue. They are all blue, so the moisture is fine. And this will be the last bag. And I need to update my bill of materials for that. My inventory. So what is pin 1 on this chip? I would suppose it's this one, because it has a corner in the edge. And the others don't have it. And here on the seal screen, the indication is here. I have a line, which indicates pin 1, and I have a dot, which indicates pin 1. And to solder, I will just put some solder here. Let's add some flux. That helps a lot, particularly if you've already added solder and it lost the flux. You want to add even more flux. I could do it by hand or with the tweezers. But the table will be rotating. I don't like that. So let's line the parts. Seems to be lined. Let's hold it down. Let's stack it. That's stacked. And it doesn't need to be clean for now. The solder can be really messy. It's not too important. The important part is that it is fixed on the corner, and this way it doesn't move anymore. And now I can make clean soldering, and we will do some drag soldering. So still add flux, particularly for plenty of pins. Plenty of flux, that's fine. And now let's go for the drag soldering. For on the side you didn't tack, because else you would remove the tack and the part will move again. So let's do it on this side. Add a bit of solder on the soldering iron, and yes, this is looking good. Let me have a look at it. Oh, yep. Maybe not enough solder on this side. But if you put too much, like I did now, you create bridges. But to create bridges, to remove the bridges, add more flux. It helps for the solder to not stick where it shouldn't. And then with the soldering iron, just drag away the solder. It likes to stay on the soldering iron rather than on the pads, because the soldering iron is just warmer. And solder likes where it's warm. Okay, this one is a pain. This side looks good. Yeah, there's one bridge here. Bridge is gone. I'll do some visual inspection afterwards, but currently it looks nice. And now that one side is completely tacked, you could actually solder it. You could solder now the tacked side, but just do it the opposite side. And this looks nice. Just a solder bridge here. There's not a lot of solder here. Tiny dot. Okay. Visual inspection afterwards will show me if I did a good job. For now it looks okay. Sorry, someone is ringing on my door. Be back in 5 minutes. There's someone who wants to meet me, so I'll be back in a couple of minutes or more. Let's see. I'll try to keep it short. Up. And we are back. Phew. I need to breathe a bit. Stream should be running. It is running. So, after this interruption, I was drag soldering. And I'm sure it is so warm here. How warm is it? Yeah, 32 degrees Celsius. That we need to put more flux. Everything evaporated. Flux. Actually, yeah. These flux cylinders, they come just with the screws, not with the plunger. And the plunger is not very convenient to press by hand. So what you can do is have this kind of clamps. Then you print this syringe mount. I found it off Thingiverse. And this clamp is now used, instead of clamping, it's used to press out the thing. And you don't need a lot of force, so it's quite convenient. I recommend it. There are other ways, but I found it good. Oh yes. With flux, everything goes. One solder bridge, like always at the end. Too much solder. Now that looks fine. This is this end and fourth one. Then we need to put all the capacitors for the IOs. So let's clean it, because there's plenty of flux. We use, and this is mild flux, we can use IPA, alcohol for it. Up. So this is just IPA, isopropyl alcohol. I can use it to clean off. And I'll clean it now instead of complete at the end, because it helps with the visual inspection. So just rub it to remove most of it. It doesn't look good, but it removes most of it. And then I use this lint-free pads. They are normally, I buy them from the nail shop, or they're meant for nail shops, where you go and make your nails. But they are very good because they are not expensive, lint-free and small. So ideal. And lint-free is more lint-free than something else, but it's not completely lint-free. So this looks now clean. See by the reflection, you see the difference. Plenty of flux, no flux. Plenty of flux, no flux. This allows me now to do visual inspection. Might be a bit light on solder, but I see the contact points. No bridge. And I soldered. No bridge. No bridge. Yeah. My drag soldering is not bad. Bypass capacitors, everything which is near it. You see C9, so they are all. Why do I have two bypass capacitors here? I don't know. But these are 100. I have to check which values they are. This, the capacitors are here. Then we have plenty of resistors. This is the divider. I know there's one resistor which is kind of important, which is the reset resistor. We'll check which one. I'll check which one it is using the schematic. But for now, the bypass capacitors. And I think I can put all the capacitors now, because they are almost all bypass capacitors, the remaining ones. So which one are the 1 microfarad capacitors? Section capacitors. 1, 12, 14, 1, 2, 1, 2, 3, 5, 6, 8, 9, 9. A bit of a pain that is here, so can I open it a second time so I can better see it on my monitor? Oh, I can use, I know. I'll leave you with the bomb and I will use the I will use the, how's it called, schematic on the other screen, what you don't see. So which one are the one? Or we can simply start one after the other. So one is 1, 2, 3, 5, 6, 8, 9. 5, 6, 8, 9. So normally, yeah, 2, 8, 6, here's 9. Let's put some solder. 9, 5, was it there also? 5, yes, 5 is this one. Ah, and I recognize it because I have 1 and 100 nano, right, like here. 1 and 100 nano, although the 100 nano should be closer. What is this one? 9 is 1. 11 is 100. I should switch both of them. The 100 nano should be closer. Don't know if it makes really a difference. And then 12. 12. This one. Okay. This is good. Because it's further away. That's alright. 12, 9, 5, 1, 3. Where are 1 and 3? 3. This one. And C1 is this one. One microfarad. And actually I could do it by hand, yeah. So in theory, if we would respect the bomb, C11 would be 100 nano, but I will put my 1 micro there, and the 100 nano will be closer to the pad. Something I need to improve on the next design, on the next iteration. Because generally, the smaller capacitors discharge faster and have lower ASR than the bigger ones, so it's better to have them close. I think so. Never tested it thoroughly though. And oh, here there's only one. Up. Then there's one here. 5, yes, 5 is one of them. Plenty of decoupling. For testing, I think we can even work without deblocking. With decoupling, we don't do a lot of I/O. This is soldered, this is soldered, this is soldered. Fine. So let's put the other one. C15 is 100 nano. Now let's put some solder on the pads. Here, here. Ah, here's one. I missed one of them here. This is also 100 nano. This is for the SPI chip, but the SPI chip is huge. I could use a smaller one. I have lots of them. The huge ones, so it doesn't bother me. These are other ones. C19. What is C19? What is C19? C19. Ah, this is an optional. It's for the reset. So this is the reset resistance. Important. And this is just for debouncing the button. I think we can, as I can remove the reset resistor and the debouncing thing in theory, and I probably will do it in the end. But for the prototype, I want to have not too many issues. This way I do it this way, I do it this way. We can still remove it afterwards. This is not important. I think most of them are here. So, this is 100. 100. C9 is 100, right? C9, yeah, this one. I've missed this one. One microfarad. Because this is one, I know that this is 100 nano. C4. C4 is decoupling. Oh, C3 is actually... I made a mistake. C3 is not 100 nano. C3 is 1. And I think I've put 100 nano here looking at... No, the color is browner, so this is 1. You can kind of see the value. So on the resistor it's useful because the value is written on top of it. On a capacitor it's not written on top, but you can kind of recognize it with the color. Seems the orange one are the 1 microfarads and the brown are the 100 nano. I don't know if this is standardized though, but this is what I've seen most of the time. C7 is 100, yes, C7, oh this is, C15 is also 100. 7 is 100. In complete theory, you shouldn't put 100 everywhere. You should calculate the one you need, but 100 is very often the recommended one. Per default, it works really well. And it's probably an overkill. You could add less, but why would you? Because 100 is very standard and very cheap. It costs less when you populate it. That's C6. C6 is 100. Yeah. It is. Okay. C18. C18. Yeah, that's 100. C18. 100. 100. C7. That's also 100. Okay. C21 and C20 are for the crystal quartz crystal. Oh, I got it right. C19, the one for the resets. And for now, the code I prepared, because this is not exactly the same. Oh, I do have code. The firmware is working, but the firmware has been done on the development. Oh, this looks really ugly. The firmware has been done on development board and not on my custom board. And the development board uses another microcontroller, another family, another model of the microcontroller. So it's not exactly the same one. But I've changed the bootloader, and at least the bootloader should work on here. So we need a 5-pin header, and we can connect the debug. 2, 4, 5, 5, debug. SMD, we just soldered the first pin. loosely up, like with tacking. We just tack the first pin, then the solder, we can put it in place, fresh, and now we can put the remaining pins. This is ground, this will be hard, even with thermals. Okay. Up. The pins are connected, and before connecting it directly, oh, this doesn't look, no, okay, it looks solid. Before putting it directly to USB or SVD, I will use my voltage meter or my power supply and provide power using the power supply. This way I can limit the current. Let's measure if there's a short. Multimeter, let's go to ohms. Between ground and 5, we have very high impedance. 10 mega ohm, that's very high impedance. So there's no short, because I don't want to fry my microcontroller. This is the only one I have. This is 5, let's set to 5 volt. Ah, it's the wrong one, so you won't see what I'm setting, because I have 2 power supplies and only one is connected to automation. And do you still see the automation? Yeah. So let's set 5 volts. 5 volt and 100 milliamp max. This way, amps, 100 should be plenty enough for what we need. This is plus, this is ground as far as I remember. Yeah, plus ground. Let's switch it on and see if it draws 100. 12 milliamps. 12 milliamps seems to be something right. So apparently the microcontroller is up and running, doing nothing for now, but up and running. So we can connect SVD to it. And for that, actually, I want to. I will remove this board. Here, right, let me get it. This is my development board, and here, this is another microcontroller which is used for the development board. And the development board comes with a programmer. It is just an SVD programmer, but I'll also use this SVD programmer. And they did it quite cleverly. You can break off the SVD programmer. That's what I'll do. Try to break it off. Up the breaking tabs. So what you lose is actually there are UART lines. So now you can connect this part to this part using these pins here. But so this is why they added the pin, so you can use this independently. What you lose is UART. This has also a UART converter, and the lines go through these breakout tabs, which we don't have anymore. But I did not use UARTs, so it's not too important. Let's now remove these tabs. So this is clean, and it doesn't scorch. I will put a header on it, 90-degree header. Do I have 90-degree headers here? No. My 90-degree headers are somewhere else. Here, SMD plus 90-degree. Here, my box with the headers. 90-degree header. Here, we need 5 pins. 5. Oh, it solders very well. So I've tacked to one pin. Let's now move it in place. Heat up again solder joints. Now we can move it in place. This way it looks straight. And we can solder the rest. And the pin out should be the same. 3TIO. Up. Oh, it solders very well. The inning is probably quite good. And this will become a programmer. Although we can use any kind of SVD programmer, I want to use theirs. And normally I should connect it this way. Now you see it's male, male, pin, pin, and I will just need a cable, 5-pin cable, 1, 2, 3, 4. So my box, Dupont cable, female, female, and I'll probably have one with 5 pins. One will use 1, 2, 3, 4, 5. Let's say this is meant for something else. It will work. It's not ideal. 1, 2, 3, 4. Let's use it. This is a quite a custom one. You see, these are the normal Dupont headers, which are square. But on the other side, I've put the shrink tube, so sometimes it fits closer to each other. But we'll use this. So first we want to identify it. If we can identify it, we will flash the bootloader. The bootloader works over USB. So then we can solder USB, but first let's try to identify it. Actually it also uses, there is an LED. Didn't put an LED. I did put an here, LED. I will put the LED. Once I identified it and I flashed it, I'll put the LED and the button, because the LED should be on when you're in bootloader mode. I can put the LED now, actually. Yeah, let's put the LED now. So the LED, the footprint is here. There is a marking on the PCB which is pin 1, but I never know if this is the cathode or the anode. I'm sure there is. Maybe the marking is always the cathode, but in this case it is the anode though. But yeah, on LED pin 1 is also always a mess. But I see there's a SIG trace going to 3.3 volt. So this is the anode where the power, the plus comes in. It goes through, yeah, it comes through the anode, it goes out to the cathode. So we'll put an LED. I will put a blue LED, which I have here. Blue, because this LED is very often used for activity. I use red for power indication, green for status indication, if everything is fine, and green for, blue for activity indication. So now I don't know what is plus and minus. You can also read it from the LED, but what I do is just use the multimeter and figure out which is plus, which is minus. Wrong way around. Yeah, you see it lights up. This side is plus, and I can read from the board that this side is plus, so I will just put the LED this way. And because the blue LEDs are very ultra efficient and you can see them clearly well, I always add a huge resistor to it so it's not too bright, because I hate really bright blue LEDs, pierce the eye. So what I do is use a 1K resistor. For red I very often use 470, for white 330, and for blue I use 1K. Plenty bright enough. So the LED, and normally if we connect USB then the LED should not light up. Let's put the marking the correct way around. Here's the marking. Okay, the LED is on there, the header is there, so let's continue. We have voltage target is ground. Yeah, it should be red, but then we just have ground, it's red, although it should be voltage target, and then the other pins orange, yellow. I don't use the colors, I just use the order now. And if I connect this, let's try to see if the LED goes on. The LED should not go on if I plug 5 volts, and the LED does not go on if I plug 5 volts, which is a good sign. And yeah, the USB meter doesn't say it's really high. So now let's try, I should have, I think it's this one, yeah. This one is a USB cable going to my computer, but now I need to start up the IDE. Let's start the IDE. New window. I'll show you the IDE. Let me start it first. Meanwhile, I can put some order on the table. So the IDE is the Cypress piece of Creator IDE, something like that. It's a Windows tool, and since I don't have native Windows, I need to start a virtual machine. And actually I only have oh no, I do have Windows for other things. My oscilloscope only works on Windows. So I also do have Windows for that. Oh, I'm starting to have your callbacks probably issues. My USB bus seems to be very crowded. Yeah. 2 callbacks passed. Yeah, the USB bus is crowded, but only since I've started this, I don't know why. So Pizza Creator, let me switch so you can see what I'm doing. bench. Up. The resistor is for the reset button. Where's the reset button? Reset R10, which is 10 kilo. Yeah, you could put 10k. R10, which is should be somewhere. Shouldn't it be R8? Ah, that's reset. R8. We should also put reset in a reset state. But normally, I think in the microcontroller, I do put a pull-up here. But I think still pull-up is not bad. R8, that's the external resistor. It's 10k. Do I have 10k? This is 10k. So let's put RA, and we need the other one, which is... let's put first RA. R8. This way. The soldering iron, when it's in the stand, it's getting really warm. Although normally it shouldn't get warm, it should switch it a bit off, but how it really is warm. The handle is warm. I don't know if the tip is warm, but the handle is really warm. Okay, for this one. And there is for the reset button R3. Where is R3? Here. This is R3. And we are not connected to USB because I'm soldering and I don't want to create any shorts or things like that. But what's the good news is that we were able to program it. Okay, R3 is connected. Let's connect over USB and check the button. That's just a 6mm button. We have a box with plenty of 6mm button. Actually, I do have even a button box with spare 6mm buttons. These ones, even plenty of them. Oh, this one is also nice because it is very flat. Let's use this one. It doesn't matter. The height doesn't matter. So see, the 6mm buttons means 6mm wide, 6mm long. And what you always change is how high this nibble is and how much force you have to put on it to activate it. These are the differences. So just put button, solder one leg. For now, maybe I want to do it directly. Let's put eye protection because I will cut some and I don't want them to fly them in my eye. So eye protection. These leads, you can also stop it using your finger, but sometimes it really snaps and goes away. 1, 2, 3, 4. It snapped. So now I need to connect it, and normally if it provides power, yeah, there's something not working. This LED should go on, and it doesn't go on in bootloader mode, and it should be in bootloader mode. So there is something not working. When I press the button when it boots, it should land in bootloader mode, and when there's no firmware, which is the case here, it should also land in bootloader mode. Let me measure. Voltage. Where's the second multimeter lead? Multimeter lead. We need ground. This is ground. Do we have 3 volts here? Yes. So we have 3 volts. Did I reverse the LED? Let's disconnect and test it. I hope I did not. So this would be 3 volts. Damn it. Did I really reverse the LED? I'm not in diode mode. Now I'm in diode mode. Okay, the LED doesn't go on at all. I think I've reversed it. Let me check on one other LED. Blue. So the small corner is on plus. The small corner is on plus. And here, the small corner is on plus. Oh, it seems correct. No, this doesn't work because everything else is draining power. Let's cheat a tiny bit. So let's provide 5 volts, and I will just connect this pin shortly to ground. This pin. Normally this pin should be operating in open drain mode, meaning if I connect to ground it shouldn't be an issue. We will try. I need a cable. Something like this to short it to ground. And I'll do it just briefly. Yeah, the blue works, although it is very dim. It is ultra dim. Not sure if you can see, I probably need a 1K is probably too much. It's very dim. Probably need something smaller. Do I have smaller? No, not at least not here. Ah, it's very dim because it's not the same power supply. Sorry. Yes, I know it's dim. I was surprised. Blue shouldn't be that dim. It's not the same grounds. So let's take a wire. I've connected the ground from the power supply. The power supply currently is not earth, so it is floating. So let's use the ground from here, and yeah, that's a lot better. This is what we should be seeing. This blue. So it is mounted correctly, so it means my code does something wrong, or it didn't configure it properly. Or it's on the wrong pin. Let's put the USB part, and let's check if USB works. Let's disconnect this, and now USB. We need two 22 ohm resistors, which we don't have yet. So let's put my box of 22 ohm resistors. We don't need a TVS yet for USB to work. We just need the 22 ohms resistors. And I really hope this, I rushed it super fast, so I don't know if it works correctly. 20 plus minus 1. 22. Yeah, 22. Let's create a new drawer for this. Up. And paper. Where's the pen? Here. So we have 22R0603, 5%, 0.1 watts, 0.1 watts. Now, I just created this sticker. This sticker. Ah, I know what I forgot. I need to fix that. Here. like this. This, I used it. I have to place it somewhere where I know, what I can tell. You have to update the inventory. So I have to update the inventory for all these parts. There's another part where I need to create the inventory. Here. There are 5 parts. These are 5 parts, and I just keep the bag. And next time I will just look at the bag and see I need to update this in the inventory. Else I might go mad. Where is the tray? The bin thing here. This, and now I can put all the 22 ohms here. There are 22 ohms, right? That's 22 ohm. That's a very common value for USB termination, although it always depends on the line impedance and so on. 22 ohm is a good start. Up. Cable is in the way. Yeah, I still need this device because I'm sure I will have to fix the code. The second one. Up. Yeah, a tip. The parts, these flip very often, so you just hit on the table until it flips the right side. One, two. Let's connect. Part correctly, so I have the surface tension. Draw the parts in the right place. Just done. Now we should have USB if I connect directly. This is missing, but this is just for protection. It's not mandatory. The path goes through it. So let's connect the USB and let's check if my computer tells me anything. And if it tells me that something has appeared over USB when I start it. Do I see my logs? No. Oh. It is there. The bootloader is there. I've seen it in the logs. It did start the bootloader. So why didn't it switch on the LED? Did I configure the wrong pin for it? So let's debug it together. But yes, I see that the bootloader has started in my journal logs. Now let's debug it, one after the other. So my bench, and that's the bench. We can solder, well, we can solder all the rest actually. Then the rest is just development, but yes, we can solder all the rest. Then let's do it. We have some capacitors for the crystal. That depends on the crystal. I don't, so the crystal I have, let me show you, I think it's an IC, in my IC box. And this is where I put all my crystals. Or maybe MCU, yeah, probably microcontroller and not IC. Up. MCU box, I have plenty of boxes. I think I have 100 of them, something like that. And you see I have the quartz crystal loose. I don't remember what the capacitance for them is, but it also depends on the lines and so on. So I generally put a random value between 12 and 18 picofarad for the clock, and it should be fine. So let's also do that. We have multi-layer capacitors. This can close. This we need to close. Probably need them. I probably need the resist afterwards. But first the capacitors. I need something which is 0603 and which is between 10 and 12 and 18 picofarads. So this is 1206. I have some remaining parts I want to get rid of. This is not the right value. No, no, no. 10 nanofarad. Why do I use 10 nanofarad? 10 picofarad. Could actually use this. This seems to look nice. 10 is probably a bit on the small side. 18. And this is 0603. So we'll, yeah, 0603. We will use this. 10 seems a bit small. One, two. Do we need other capacitors? Oh, there's one capacitor here, but this is an 100 nanofarad bypass capacitor. And this crystal is huge. I will put, on the next one, I will put something which is like a fifth of them. Ah, this is hot. With it a fifth of this size. Tweezers. Here, tweezers are here. This is 18. So my bootloader uses the internal oscillator, which is here. And this is precise enough for the USB work I'm doing. I have an external oscillator. So the internal oscillator has something like 1%. It has a 3 megahertz internal RC oscillator with 1% error. That's quite a lot, 1%. This is why I've added an external quartz crystal, which is like something 100 ppm, parts per millions. A lot more precise. And when you want to do some fast protocols, which currently I'm not doing, this is quite important. Although I am. The UART detector. The UART detector can go up to I've tested it up to 1 megabit per second. If you want to do this correctly, it's good to have a precise part and to use the external oscillator. Although the demo code I did, which worked up to 1 megabit, used only the internal oscillator because the evaluation board only has the internal one and not an external. Up. Capacitors are there. Now let's put solder on a pad all along. This microcontroller, this thing is annoying now. And I have the bootloader to, yeah, I will disconnect it. This is annoying to solder. I have the bootloader which is working, and the bootloader is good enough to flash the firmware, which is not ready yet. One side, one. Up. Now, here we have 100 nano. The flash uses 100 nano, and it uses also plenty of other things which are not mandatory, but I've added for debugging. Once everything is working and done, I will desolder parts, and I will still try if it works. And if I desolder the parts and it still works, then I know that I can get rid of that. Although not all the parts. I'm sure if I desolder some decoupling capacitors, it works most of the time, and I will not detect when it doesn't work. So I will leave them on. But something like pull-up resistors and things like that. Oh, this capacitor doesn't look nicely soldered. No, let's get rid of it. Let's put a new one. And some flux, because the pads are now too mushy. Where's my flux? Yep. So, yeah, so there is flux in the solder wire, but this is the white fume you're seeing. So when you solder too much the solder, when you heat up too much the solder, just get away. And to solve it, you just add new flux, and then you can resolder the parts correctly. And this solder joint looks much nicer. Yep. So, what else do we have? I'm sure we have 0 ohm resistors. 27 and 28. Let's finish this. Yeah, let's finish this one. 27 and 28. Let's solder this one first because it's in the middle. This is a flash chip, and the flash chip is an IC. This can be closed. We don't need any capacitors anymore. IC, my IC box, and I should have a bag. Plenty of flash chips. Yep. Flash. Very inexpensive. Outside of the microcontroller, flash is very expensive in the microcontroller because these are different silicon die technologies, and mixing them costs a lot of money, or combining them, it costs a lot of money. So let's tag one part. It's not aligned correctly. Better. Okay. The other, and I already see that it is not very convenient to solder it. So let's add some flux. It's old parts, so the leads have probably corroded since then. Oh, a lot easier. Didn't do any drag soldering though, because the pads are really wide, so you don't need drag soldering, but you could. Here I'm soldering the pins individually, and this way I can see the nice fillet between the toes. So now the slashes here are 27, R28, and I'm sure these are 0 ohm resistors. Yes, they are. And I'm sure I have no 0 ohm resistor here. That was to be expected. So, 0 ohm resistors. Add a new sticker. And I don't have a lot of components in my assembly tray because the assembly tray is quite recent. And I didn't make a lot of projects in it. It's probably too large, is it? Yeah, too large. Oh, too large, too big. So we have 0 ohm 0.603, 5% and 0.1 watt, correct? Then there's the ppm, 200 ppm, but that I don't care. 5%, 0.1 watts, 0.1 watts. This I don't need anymore. Will I put 0 ohm here? No, I'll put it this way. These are more debugging resistors. And yeah, the 0 ohm resistor just here because I've never tested tying the reset and the write protect directly to the pins. In theory it works. In practice I didn't test it. This is why for now I add 0 ohm. If it works with 0 ohm, then I will have wires directly and not resistors anymore. This saves a lot of space. Where is the tray inserting thingy? Yeah. Tray inserting thingy. Funnel. That's the word I was looking for. Let's put plenty of them. I have, how many do I have? 1000. Oh, this is quite rare. My power station, power supply, I've modified the power supply so it has a fan, but the fan only turns on if the temperature of the voltage converter. It's a switch mode power supply which is integrated in the power supply itself, which was actually the power. And I've modified so the fan is not always on, but as soon as the heatsink is at 50 degrees, it is on. And now the fan is on, meaning although I don't use the power supply at all, and there's no short, it is so warm here. Yeah, we are still 33 degrees Celsius. That it went above 50 volts, 50 degrees Celsius. So here the 0 ohm resistors, let's solder them. 0. Let me clean up a bit my bench. Scissors here, pen here. That's okay, that's trash, I don't need this anymore. I have plenty of humidity indicators. That goes here. Better space, now I can move freely my soldering iron. Tweezers. This looks ugly. Up. Now you're correctly there. You should be in place correctly here. Another lot of components remaining. Are these 22 ohm resistors? I don't remember. Yes, they are all 22 ohm resistors. We can add them now. We will add this one. R29. R29, its parts. What does R29 do? It's 1K. It's a pull-up. So it's 1K, but I think I want 1%. I should have added to the schematic when I want precision parts. I think it's not too important though. No, it's a test points and I will measure it. So in theory, I don't need one. Oh, I do. So it's 1K precise at 1%. And so here I have 1K, but 5%. I need 1K at 1%. A precision resistor because I do kind of precision measurements. And here's a roll. And that I will not add to the tray because this is not something I use very often. It's not a very common part. Although I have plenty of space, but I'll keep them in the roll. How many do I have? 1,000. Yeah. I can also add that. Let's add it. There are plenty of space and they don't cost much, and I have plenty of them. Resistor. That's trash. That's trash. And then there's 10K, which is also 1%. And they are all 0. Oh, this is 100 ppm, so this is even more stable. It's not 200 ppm. So this is. Oh, you're not seeing what I'm doing. Just writing the label. 1K, 1%, 0, 1. 1K 603 1% 0.1 watts. And then I need the same with 10K, right? Yes. 10K 603 1% 0.1 watts. So let's fill it. New tray. In the bin. Oh, starting to get too large. In the bin. Okay. This way. Where is the beginning? Where is the they've added tape. So I've never used this part yet. This roll up. I'll probably never need that many. Yeah. At least I don't need to refill it. Up. And how do I store this? Do I need to put tape? Yeah, I need to put tape. 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 Up. And then I need a 10K. the other bag. Up. That's 1K. This is everything above 1K. I should have 10K at 1%. 5K, 6K, 10K, 1%. Yeah. And yeah. And here they didn't specify, at least on the label, they didn't specify the temperature rating. But I'm not doing that pressure thing, that precise thing. So, plenty of 10K. Up. And at some point I'll probably stop having 3. I'll probably get even more precise, no, although I have plenty of rolls, but at some point I'll stop using 5% and I will only use 1% because they're not too much more expensive than 5% resistor, and this way I don't have 2 parts, 2 trays for 2 parts. So the next time my 5% resistors are empty, I will just get 1% resistors. It's not worth having 2 boxes. Come on. Close box, close. This is trash. Up. So we had first R29. R29 is 1K, if I remember correctly. Yes, R29 is 1K. This is the pull-up resistor I'm using to actually measure the target pull-up or pull-down. I'm using this 1K. That's the 1K. Let's put some solder on the pads. And sometimes, yeah, sometimes on the you're not seeing anything there. Sometimes on the top of the resistor you see something like here you have 102. This is 1K because it's 1 0 and then 2 zeros additionally. And sometimes you see something like 01B, and 01B also stands for 1K. I don't know when they, if this is interchangeable, or if 01B also means that it is 1%. That's a good question. Or if it's just 2 different ways of marking 1K. Too much solder. Up. Now 10K. These are this one. I need 3 of them. And this creates, the 10K here now creates a voltage divider, and I use this voltage divider to figure out if the external voltage is connected or not. If the external voltage is not connected, it will switch off all the outputs and put the inputs back into protection because the power domains are not provided to the I/O pins. And this is done in hardware. Using a voltage comparator, and then there is just an interrupt routine. So I don't need to check in software all the time if what the voltage is. There is a voltage comparator which is in the analog part of this chip. Quite useful. Actually, maybe no. I still need the interrupt service routine because it's not only switching off some pins, it's doing a bit of more logic, which is probably not doable just with hardware. Because in theory, you could have some digital logic implemented into PySock without having any code. That's also possible because there's some kind of CPLD FPGA in it. come on. I need to use flux for a resistor because it doesn't want to go in place. Okay, then I will use flux. Can't get rid of it afterwards. This is because of my bad soldering skills. I know, because the other pad is ground. This is why it's so hard to put in place. And the handle is really warm. This is not normal. I should have a look at the IR camera how warm this is. This is unusually warm. Okay, now it's correctly in place. The ground pad was a bit in the way. Here is at least we are done almost with all the parts. These are just, this is the test point where I can measure externally the voltage. These are just 22 ohm resistors, and these are the TVS diodes. And then we have this part. And I have too much solder on this pin. Let's clean it up. Looks better. So, plenty of 22 ohm resistors. Let's go. By hand, it's not fun, but doable. With solder paste, it's probably easier. But we've started doing it by hand, so we'll finish doing it by hand. Up. And here. 22 ohm, they are here. My tweezers are getting sticky. 22.0. Yeah, the tweezers are getting sticky. The part is holding onto it. It means that I need to clean the tweezers. Pad, or wipe, and let's clean the tweezers. Probably it's just has plenty of flux on it, which is kind of sticky. That should be better. Now does it stick? No. Now the part flows off. That's how I want it. Up. I need 16, so let's put the 16 out. 2, 3, 4, and it sticks again. 5. Oh, that's a lot. Particularly when you can grab them. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we'll probably use hot air to level them. Let's try that. Let's try actually. I'm in a mood of playing a bit. Oh, no, I didn't prepare it. I don't have, oh, it is, here. I do have a very old, so this is a syringe with a solder paste, very old solder paste though, and it's good that now it's warm, so I don't need to preheat it. And now using this solder, the wrong way around. Now I can add solder on the solder pads. not very clean. Should work though. Works better from this angle. Oh, sometimes there's a lot of it. Doesn't look clean. I've never tested though these things. So the first ones I need still to solder them by hand. Part is flipped. Okay, here is too much solder. Far too much solder. Let's see if it's will glue together. Solder paste, I mean now. Let's put all the resistors to the right orientation. Normally text, okay, wrong idea mixing both of them. Normally it's really tacky on the solder paste, but now it's not because there's a bump on the other side from the solder bolt. Shouldn't have mixed the combination, mixed the technologies. Up, up. Come on, tweezers. Let's clean the tweezers, they don't let go of the part. Ah, do I need a second tweezer just to get rid of the parts? Let's use the probe. Yeah, I didn't win any time. Who cares? So we will surface solder when you have plenty of. We will solder using hot air. When you have plenty of parts, it's a lot faster. Now the components look crooked, but I hope they will go into place. Once I heat them up, I have one resistor much, or they go into place once I heat it up, but I'm not sure because of the other solder. I'll try it out. We'll not do surface solder on this thing because this is plastic. We'll do it on, so let's remove this. We will do it on this phone holder bracket. Tack, tack. Switch on the hot air. get the hot air, and I'm sure it will look messy. And 350 degrees, around that, to 400 degrees. Let's put less air, and oh, it's still too much air. And let's try to heat it up and see how it looks like. So first you heat slowly everything, so the flux in the solder paste has time to make its action. And then goes into place. And then surface tension does the rest of the job, and here there's not enough solder. I wasn't precise. And I'll do it by hand. And here is far too much solder. This looks nice. This is reversed. Let's put it the right way around. That's okay. So it does work. I didn't expect it to work that well. Now let's have it cool it off slowly, and let's fix things by hand where there's too much solder here. I just hope that no solder is under the still too warm. Still warm. Come on, cool off. Damn it. I've lost plenty of solder. I didn't back off. And what does this solder actually? Yeah, it is lead free, but who cares? I'm soldering with lead. Let's cool it off and clean it. Oh, yes, it was warm. And I want to measure all of them to see if they are shorted of their 22 ohms. They look good though. So let's, yeah, we can measure them in place. Up, ohm. We'll do the rest, not with hot air, but with solder. But I've seen it, at least you've seen it. Here, this is one lead. I need the other lead. And let's measure it. I don't need this anymore. $22, that's fine. 22. Let's do it this way. 22, okay. 22, okay. 22, okay. That's okay. That's okay. That's okay. That's okay. That's okay. Oh, no short. I thought with the ton of solder paste I've added because it's so warm, there would be at least one short underneath the component. But they're all at 22 ohms. I'm a bit Ah, no, this one is also soldered. Let's check the pin. This one, yeah, that's soldered. Yes. Yes. Oh, damn it, it worked better. I didn't add too much solder paste. I wanted to show you how to fix it, because if you put too much paste and not everything has place on the pad, then it will, some small solder marbles, some solder bolts will be beneath the resistor and kind of could make a short, which is a pain because you cannot see it on top. But it didn't happen. That's just a lot of luck. So now we need to add all the TVS diodes, which are there to protect the inputs outputs, and they are in diodes. Here, my diode SMD book. Up. And where are these TVS? Should be somewhere in the back. These are 2 bits, and it's something with 4 bits. It's these ones. And I need some of them. 1, 2, 3, 4, 5. One, 2, 3, 4, and 5. Come out. 5. Now we can solder them. And I need to figure out, this is pin 1. Then we can test USB again, and then I just have to test the firmware. And because I'm too lazy soldering correctly, and I think it will be a pain to solder correctly all the things by hand, I will add flux individually, all the pins individually by hand. I will add flux. It's a lot easier to solder, because also it makes the flux not bridge, the solder not bridge between the pins. And flux is good for surface mount. Up. Let's solder. I need to press this one down. Too much solder on my iron. Okay, that looks nice. Last part. Visual inspection, correct quickly, just to see no solder bridge and solder on all pads. Yes. Now we need to solder the last parts. This header, I shove it somewhere here. Is it? Yes. No. This is 90 degrees. Do I have only? This is only 90 degrees. Up. This box. Header, this fits almost nicely, but not completely. So let's take another one. Up, cutters, and we need 1, 2, 3, 4. 1, 2, 3, 4, 4 times 2. One of the pins slightly bent. This goes here. Solder it. Oh, and I didn't show you. This is the solder I'm using right now. You don't see anything, but this is SN1663 PB37. 37. Sorry. So it's lead based, but the most important part it's 0.8 millimeters, and for fine soldering work it's good. And on soldering iron you can really buy cheap soldering irons and they will do the job. That's not the same thing on solder. On solder, don't buy the inexpensive first thing cheapest one you find. Somehow, although the quantity of metal is always the same, the flux and the mixture makes a huge difference, and it's not fun with cheap solder wire. So buy some branded solder wire. Don't care about the soldering iron. This is really not important, the soldering iron. Even the cheap ones will do a good job. The most important part is the solder wire. So now the last part, the 20-pin connector. 20-pin IDC 20-pin. I should have some 90-degree ones. Yes, I do have some. So this is my box of IDC connectors, some IDC connectors. There are plenty of other ones. This is the 20-pin IDC connector. It should somehow fit. If not, all the pins were bent. Come on. Up. Oh, and actually, that's kind of a feature. I don't know. I did cut the board, so I will have it at this level, so it's not too high. Yeah. So the level of the case, I didn't think about it having it the same level as the board, but it makes it look nice. There's one pin which is a bit too, no, it's good height. Let's make the other pin same height. One. Let's fix this one. Now it's the correct height. Now we can solder all of them. It's not very straight, but it's good enough. Up. And like always, with these wires, when there's lots of fumes going out, just blow on it so you don't inhale it. Not sure if it's an issue, but I'm sure it cannot be something good. This is ground, so it takes longer. flow into it, and the rest. Do I want to cut the leads? Because they're really high, really long compared to all the older ones. Because now the connector is at the same level as the board, the leads are super long. See how long they are? But that's because I've went too low. Yeah, let's cut them. Safety glasses. Use the stronger plier, not my side cutter. Yeah, stronger plier, and let's cut them off. And my finger is kind of preventing them to go flying everywhere. Up. All the pins go in the trash bin. And if you, I've lost some capacitor resistors, I'm sure they're just from here. If you want to be clean, you could actually resolder them so they make a dome and not these crappy things, but that's good enough. What's missing is just a jumper. Let's get rid of these glasses. Jumper. Here, because you need a jumper to select the target voltage. Plenty of jumpers. And voila, the board is assembled. Just have to clean it. So to clean it, plenty of alcohol everywhere. Then we will scrub it. Oh, what I can show you also is another kind of scrubbing, which are quite nice. I don't have a lot of them. I need to buy them. These kind of swabs. These are not cotton swabs. They're also made of a fabric which is lint-free. And for scrubbing and cleaning, they're really nice. I don't know where I both just look for swabs. I think they're medical swabs for something, but they clean really nice because they are kind of a sponge. So they still they absorb the thing on the board, and they have enough flux IP on it to clean the rest of the parts. I recommend them for cleaning, and it leaves a smooth surface. So if you want just targeted cleaning, use this, because this is super inexpensive. This is more expensive, but it does a really nice job. You see the nice job it does? This looks super clean. Can also do the back side, because we want a clean board. On pins, you have to pay a bit more attention, because it demolishes the swab, which is not ideal. It still hangs, and no lint on there. And yes, this looks clean. Let's focus. And this is the final board. See this bit of trace of the alcohol? This will evaporate. And with that, it is soldered. So let's connect to USB to see if it still works. And if it still works, soldering is done, and then just need to develop the firmware. Finish developing the firmware and testing it. So, yes, USB hub is still, USB is still connected. I see this still detecting the bootloader, and there is this. So there's no short, anything. With that, the prototype is finished. Now I need to spend more time to port the firmware to this microcontroller family to this device, and continue on there and finish the firmware developing on it. But for now, it seems to work. And this will end the stream. The next stream, I will show you if this actually works correctly. If the device works as expected, and if I can find JTAG, if I can find things like that. I've never tested the SPI yet, the SPI memory. I can continue developing on it. For now, I just want to port the firmware, and the firmware can only detect UART, SVD, and JTAG. But that's the main part. All the other things are just features which can come later. So I'll let you know in the next stream when I've tested ported the firmware and we can test it. But for now, we are done. So enjoy and see you next time.